And yeah, I would like to give a brief overview of how we see the topic of circular economy from a structural design or structural engineering perspective, because that's my background, and that's also the activity which I research and educate at the university, but also run in my own private company here in Berlin. So obviously, in the last couple of years, there were many political important decisions, which we all know about. So there's the Paris Climate Agreement, and also the Dutch government decided to have the circular economy in 2050, which of course is a very ambitious goal, but I think it also creates a lot of opportunities for us as architects and engineers and designers to contribute to a good sustainability in the future. Then, of course, apart from the Paris Climate Agreement, we all know the Sustainable Development Goals from the 17 goals. Because not all of the 70 goals are directly related to the built environment, but I think most of the goals are somehow related. And of course, we can see and we can try to contribute to these goals to achieve it in the near future. And then, of course, more recently, there's also the European Green Deal. And of course, this is also not only about the built environment, but of course, the built environment is a very important part in the industry and in the society. So again, I think it's on the one hand side, of course, a big responsibility of architects and engineers to do something in that field. But I think it also creates a lot of opportunities for us as researchers, but of course also as business to develop. Of course, there's also some kind of discussion between energy and material resources. So if we look back in the last 20 years, when obviously the whole topic of sustainability in the built environment is not new. There were already many discussions, but the focus was mainly on energy and not necessarily on material use or material resources. But actually, energy is not really the problem, because of course not in theory, but practically speaking, when energy is there, and of course there are technical challenges, there are maybe economic challenges, there are also political challenges to use the energy from the sun, but basically the energy, we just have to use it. But there's a big difference between energy and material, because material resources, they are limited in contrast to the energy from the sun. And of course, we can exploit the earth and use fossil materials, but of course, these materials are limited and there's no possibility to extend it. And of course, we can think about renewable materials like timber or other bio-based materials, but that can of course only cover part of the demand in the construction industry. And at the end of the presentation, I will show also some developments where we are also involved in the use of bio-based materials. But of course, fossil materials are limited, and that's why we have to see how we can deal with them in a good way. So this diagram from the European Union also gives I think, quite dramatic overview about the importance and responsibility of the construction industry, which is here on the left-hand side. So on the horizontal axis, you can see different industries and the raw material use, which is used in the different industries. And you can see the construction industry is by far #1, and maybe maybe in sports you want to be the #1, but in that diagram, I think we don't want to be the #1. And I think we have to work on it to at least reduce this requirements a lot to be maybe comparable to other industries. And this diagram relates a little bit to my comments about the use of energy versus the use of materials. Because, yeah, as I indicated already in the previous slides, in terms of energy use, there were a lot of developments in the last 20 or 30 years. So the amount of energy which is used to operate a building was reduced a lot, and still will be reduced and will be more or less zero in the future. But of course, the embodied energy, which is necessary to produce and to transport the materials, is not going down to zero. So this shows that the balance between operational energy and embodied energy changed dramatically over the last, let's say, 50 years in that diagram. And so I think that's also a reason to really be careful with the materials and try to optimize the use of materials in the future. And yeah, probably most of you heard about that. Even sand is a limited resource. Of course, if you look in the desert, you think maybe sand is unlimited available, but the mechanical properties of sand are not, of the sand in the desert are not necessarily good enough or to make concrete out of it. So that's why even sand is a material which seems to be unlimited is limited. And there's a very good book, The World in a Grain, and if you're interested to hear more about that, the sand story, I really can recommend that book. It's really interesting to see that, of course, sand is not only used in the construction industry, but in more or less any industry, and that there are difficult and interesting discussions are going on about the use of sand. And this is the result of a small study by the Institution of Structural Engineers from the UK to indicate the responsibility of structural engineers in the whole process. So you can see here different possibilities where every individual person can save CO2. So of course you can avoid flying, you can avoid meat and drinking beer, and then you can stop driving car. Of course, everything helps a little bit. But if you look at the possibility which you can have as a structural engineer, if you try to develop optimized structural system, the amount of CO2 which you can save per year is much, much higher than all the other possibilities. And I think that's really, again, a good opportunity for structural engineers to give a good solution in these discussions. So in principle, I would like to show three possible aspects which we research and study at the university. So on the one hand side, we try to reduce the amount of materials, then we try to reuse either the materials or components or whole buildings. And last but not least, we also work with renewable materials. And obviously timber is a well-known renewable material, but in our case, we work with hemp and flax fibers and try to develop composite materials to create new structural applications. And this is just one of many examples. This is a master thesis of one student, actually two students who studied the possibilities to optimize the geometry and also topology of a structural system, and that kind of the small canopy. And of course, if we are able to reduce the amount of materials which we need for a structural system, that of course also already helps to make the structural design more sustainable. But of course, this is a very nice student project, but if you are looking around in Europe or worldwide, that's of course the reality. So typically we don't have really optimized structural systems. And if you look in the normal building structure, there's really a huge amount of material in the walls, in the slabs, in the foundation, etc. And actually the utilization of these structural elements is typically less than 80%. So I think there's really a huge optimization potential to reduce the amount of material and by this also reduce the amount of embodied energy in the structural systems. And this is, for instance, one small study which we carried out in my office for a private project in Frankfurt, where we studied different slab systems, not only from a structural and from a financial point of view, but also from an ecological point of view. So we did a small LCA comparing different kind of structural systems and tried to convince the client to go for the most ecological system, which is in that case is a bubble deck. And even if the costs are a little bit higher compared to a conventional system, the client is going this direction, and the project will start on site early next year. And another, I think, quite important aspect is the discussion about the loading on a structure. So if we nowadays design a pedestrian bridge, the typical life load, according all the Euro codes in all the European countries, is 5 kilonewtons per square meter, so 500 kilograms per square meter. But if you look at that photo, so that's the 50th anniversary of the Golden Gate Bridge, and obviously the bridge is pretty crowded. So the life load, the estimated life load on the bridge here is less than 3 kilonewtons per square meter. And if I see that picture and I know, okay, this is around 300 kilograms per square meter, then I really ask the question, why do we have to design every pedestrian bridge in Europe with 500 kilograms per square meter? Because that's quite obviously completely over-designed, over-dimensioned, and it's really a waste of additional material and resources. So again, there's a huge optimization potential. So that's one possibility to reduce the amount of materials. The second topic which I want to mention is the reuse. And I think if you're talking about reuse, there are 3 different levels. We can think about reusing materials. We can think about reusing building components, and we can think about reusing buildings as a whole. Of course, there's a strong relation to the circular economy, and I'm sure everybody in the audience knows these kind of diagrams, so I don't have to explain them in detail, just to point it out again. Reuse at material level. So at the previous conference, somebody had the code design, so I like that. And as already mentioned in the previous presentation, of course, it can happen that buildings are already demolished after 16, 20 or 25 years, and obviously that's quite ridiculous and shows that it's a bad design or bad decision. So I don't know the details of all these kind of individual situations, but of course we should try to avoid that the building is demolished after 20 years. But of course, at least if we demolish a building, one possibility is to reuse the material. And in the last couple of years, there were quite some developments about recycling concrete, but of course it's not so easy to do it in any case. But of course, a lot of work is going on in that area. So the second level of reuse is not the reuse at material level, but the reuse of component level. And I'm sure at least all the people from Eindhoven, they know this picture. That's the roof station, the roof structure at the train station in Eindhoven. And actually the trusses here are so-called Bailey trusses. And these Bailey trusses were used in the Second World War as military bridges. Or okay, they don't need mobile military bridges anymore, and we can reuse it as a structural system for the roof structure. And I think that's a quite nice example of applied circular economy. Obviously, at a time when nobody talked about circular economy, because the roof structure is older than that term and all the recent discussions. But that's why I also like to show this example. And at the moment, we also work with a couple of master students looking into that topic. So this is a master student who finished 1 or 2 weeks ago. So in that case, so in contrast to the train station in Eindhoven, he looked in the possibility to reuse precast concrete panels from existing buildings which are not used anymore, and looked at what are the boundary conditions or what are the restrictions if we are reusing elements, when obviously the connections and the way the elements are connected is quite critical. And then he tried to develop new designs using the existing elements. And the third level, so after the material and the component, is really the reuse at building level. So this was also studied by a student. So in that case, the student, she looked at different buildings which were either demolished after a certain period or they were reused. And this was then studied in more detail, and we looked at different building layers, like the site of the building, then the building structure, the skin, surface, etc. And we developed different indicators to evaluate the potential transformation possibilities of existing buildings. And so based on this kind of evaluation matrix, the student actually developed a kind of flex score, which is basically a number which defines the possibility or the chance that the building can be reused in the future. And in that diagram, you can see here on the horizontal axis the service life of the building, and on the vertical axis the survival rate. And you can see, okay, the buildings with 10 or 20 years, they have a survival rate of 100%. But then after around 25 or 30 years, the first buildings were demolished, and with this evaluation method, we could show that the flex score of the buildings which were demolished is lower compared to the flex score of the buildings which were transformed, and then of course they have an increased service life. And I think that method could be developed further in some kind of tool to help owners of existing buildings to get better decisions if a building should be demolished or if a building has the potential to be reused and to extend the service life. And okay, this is just to summarize this famous diagram, and probably, yeah, of course you know it, and I think more or less everybody of the previous speakers already had it in the presentation to detail. Yes, this is just to summarize. So on the one hand side, there's the fossil materials, which I mentioned before, for instance, how to reuse them. But of course, there are also renewable materials, and this is the last part of my presentation. So what are the possibilities to work with the renewable materials? As I said in the beginning, of course, timber is well known and used for a long time, and of course in other areas of the world, bamboo is maybe also interesting material. But what we did is to look at the possibility to work with hemp and flax fibers. So in 2016, we got some funding from the 4TU organization, and together with Delft University, also Advanced University of Applied Sciences and one industrial partner, we could design and also realize this small pedestrian bridge here, which was then installed on the campus of the university, and which was then used for a couple of years. So in the meantime, the bridge is taken away again because we have another new research project where we have the possibility to implement new sensors and also a new health monitoring system in order to get a better understanding of the long-term behavior of these materials. Because, yeah, of course, the experience is still little compared to steel or concrete structures. So here are some images during the production process. So of course, in that project also many students were involved, so we had the possibilities to have a 1-to-1 scale mock-up, which you can see on the left-hand side. So the core is a PLA foam, so it looks like plastic, but it's also completely biodegradable. And the core is in that case used as the lost formwork, and the brownish material around it, that's the bio-based composite consisting of hemp and flax fiber and a 56% bio-based resin, which created at the end a stiff structure. And because the bridge was then built on a public space, we had to follow all the regulations with the authorities. So, of course, we had to apply the Lifeload of 500 kilograms per square meter, which I mentioned before. And we also had to follow the normal rules. We had to get a building permit, and also we had to submit all the structural calculations to the authorities. And in order to get permission for the building, so on top of all the calculations we carried out, the authorities required that we also do a 1-to-1 scale test. So that's what you can see on the picture here. So in the lab, we loaded the structure with these water tanks, and in total, we loaded the bridge with 500 kilograms per square meter. And for the authorities, of course, it was important that the bridge can carry the load, and yeah, we could prove it. But for us, of course, it was even more interesting to see how the structure behaves. So because also in that bridge we already integrated a couple of sensors which can measure the strain in the structure. So we had the possibility to compare our computer models with the real model, and we could see that there's a really good match between the real bridge and the numerical computer model. And so that's why it was relatively easy to convince the authorities to get the building permission. So after the test, the bridge could be installed in one piece. So it's 14 meter, and so there was already an existing bridge. So the foundation, etc., everything was there. So we just could lift the bridge with a crane and put it in place, and then it was ready in a couple of hours. And as I mentioned, we have integrated sensors in the bridge. So also over the last couple of years, we did a couple of tests using either steel weights or people walking over the bridge. And there we collaborated with a company, Common Sense from Belgium. So they have the possibility, basically, they just plug in their laptop to the bridge, and then we can measure the structural behavior in real time and see what changes over time. But this is still ongoing research, and yeah, we will continue with this for the coming years. And then based on the bridge we realized in Eindhoven, this was also the basis for a larger European project, an Interact project, which is a collaboration between 14 partners from France, Belgium, the Netherlands, and Germany. So we started in March this year, and we are now in the design, at the end of the design process of one additional bridge, which will be realized in Almere next year. Because in 2022 they have the big World Garden exhibition, and the bridge will be part of that. And then in 2021 we realized the bridge in Almere, and then in 2022 and 2023 there will be two more bridges, one in Germany and another one in the Netherlands. But apart from this hemp and flax, we also of course look at other bio-based materials. So there are quite interesting developments around mycelium, and from a structural point of view, of course, the strength and the stiffness is relatively low, but of course we can still think how we can apply it, for instance, as insulation materials, or again as lost formwork to create composite structures. And last but not least, some of you probably also know these kind of structures. One of our colleagues, Arnold Bronk, is working with ice structures in the last couple of years, mainly together with Harbin Institute of Technology in China. And I think these are also nice examples of circular structures, because these buildings are built out of ice. And of course, they stand there for a couple of weeks or a couple of months, but then if the spring or summer comes, these structures just disappear and go back to the natural circle. So that's already the last slide. Thanks for your attention. Of course, if you have any questions, just let me know.